So here's a sample problem or example. Okay, I'm going to throw you right into the inclined plane. Because I think you guys, the trivial explanation, I don't think you guys need so much. Here's our inclined plane. We have a crate, and it's at an angle theta, or it's an object. It's at an angle theta on its on this inclined plane. Okay, the mass of the crate is 20 kilograms, and the coefficient of friction, okay, is 0.0483, and I just made that up out of thin air. Justin. Yes, that would be the mu s would be static. Good call. Okay, that does equal static friction. All right. My question to you is, at what angle does our box begin to slide? At what angle theta will the crate begin to slide? And notice I fixed static friction there in a minute. Yes, Corey.
What are the units of mu?
Good question. Mu is a unitless value. It is strictly a number because its force equals a coefficient times another force, right? So it can't have units. It has none. All right? Okay, so this is the question. So let's work it. Let's work the question. So the first thing we do is we follow the procedure. Step 1, cut a hole in a box. All right. So here's our diagram again. 20 kilograms. Mu is 0.048. So we're given the mass of 20 kilograms and a mu of 0.48. Find theta at which the crate starts to slide. Solve. We need to create our force body diagram with our crate that is on the angle. So we start labeling our forces. We have 3 of them. We have mass times gravity, we have normal, and we have mu times the normal force, which is also equal to friction. Yeah? Okay. I kind of jumped the gun on that one. So, we have 2 forces that are already orthogonal to each other. Those are the directions that you should be making your axes. So you only have to resolve one vector. Okay. All right. So, the dotted lines are those 2 axes. If you can see, I kind of drew them in. They're really faint. But those 2 blue lines are gravity resolved along the x-axis, which I took to be, which I didn't draw it in there yet. I took this direction is, that was nice. That's positive y, and that's roughly positive x. Okay. Okay, that is the same angle theta, and if you need me to show you y again, just think about the opposite angle. Just think about the angle that the crate had to rotate up, and from vertical, if that's vertical, this angle is the same as that angle. So this is the same as that theta. Does that make sense, you guys? No?
Yes.
Okay, so the theta that's on the inclined plane is the same thing as the theta between the vertical gravity vector and the mg vector next to it, which would resolve to mg cosine theta. It is next to the angle. Mg is the hypotenuse, therefore that side is going to be mg cosine theta. Okay, which makes the other vector over there mg sine theta. All right? So the sum of the forces in the x direction are mu times normal force going up the incline and mg sine theta going down the incline, and that equals 0. Then we have our forces in the y direction, which are a normal force plus mg cosine theta, which also equals 0. So we're going to solve for n. We want to find n for the y's, so we can plug it into the other equation to solve for our theta. So n equals negative mg cosine theta. That n gets plugged in up there. So mu equals, so it's mu times negative mg cosine theta plus mg sine theta, and all of that equals 0. Now check this out. This is like wicked cool math here. I'm trying to time it so that every ding is a new line to our equation. Okay. Negative mu mg cosine theta plus mg sine theta equals 0, or those two terms equal each other. So sine theta is going to equal mu cosine theta. I skipped a step there, moving it over, but you follow that? If we divide both sides by cosine theta, well, looky, our mu actually just equals our tan theta. So mu is going to equal arctan of our coefficient value. So theta is going to equal 25.8 degrees. And that's how we solve. That's an example of how we solve these problems.